Okay, in this video I'm continuing as the second video in Chapter 5 talking about loss mechanisms in optical fibers. And what we'll do is we'll break this up, we'll break the loss mechanisms up into three different categories. Fairly standard way of doing it. First is absorption. And this absorption loss is a major factor in fiber optics communication systems because it really dominates and it really determines this sort of window of wavelengths from 1 to 1.5 or 1.7 microns because for wavelength shorter than 1 micron we have large losses, that is in the UV spectrum, and for lambda greater than 1.6 microns we also have large losses, and that's in the IR. The 1.6 for wavelengths longer than lambda 1.6, part of the reason we have this is due to the silicon oxygen bond. But in general, absorption is due to impurities and atomic defects in the material. As well as just intrinsic loss due to the material. Okay, so absorption losses are really a major factor in the loss of fibers. And another major factor is scattering. And there are two types of scattering losses generally, and they're characterized by the size S of the scattering center. And so scattering means that you have imagine a wavefront incident upon a material that has some sort of inhomogeneity in the refractive index. Okay, so refractive index, inhomogeneities. And this is something that comes right along with the formation of glass as an amorphous substance. And so what we'll get is we'll get density fluctuations due to that amorphous structure with S much less than lambda. So when the scattering center is much less than a wavelength, we get what's called Rayleigh scattering. And this is what makes the sky blue, for example, and we have the attenuation is proportional to the lambda to the minus 4. And so we have much higher losses in the UV. Okay, and we can also have various types of other refractive index homogeneities with the scattering center size more or less proportional, more or less on the order of the same size as the wavelength, and that will give us an attenuation A, which is independent of the wavelength. Okay. The final category of losses is, and I'm sort of running out of space here, but I'll see if I can sneak it in here, is geometrical effects. Just very briefly, we've got two of them, macro bending and micro bending. With macro bending, typically if the bend radius is less than or on the order of 10 millimeters, we'll have a problem with macro bending. You can't bend the fiber in too short of a loop. And the idea is more or less that if you're going around the bend like this, then the zigzag angle may effectively be larger than the critical angle due to the bending geometry. Okay, the zigzag angle is measured from the interface, but as the core is bent around, that angle changes. And if you get if you get theta greater than the critical angle, of course you're going to see very large losses there. Another way to interpret that is to think of the mode profile. Think of the lowest order mode profile going around that bend. You can also interpret the macro bending losses as the velocity needed to go around that larger bend radius exceeding the speed of light, in which case obviously you can't sustain that mode, and so the mode loses power. Micro bending is a situation where when you're creating cabling, you are destroying the cylindrical geometry. And you get micro bends when you put sheathing, let's say cylindrical geometry is destroyed by sheathing. That is a tight buffer is also called. Okay, so in order to protect the fiber surface, you put a tight buffer sheathing on it. And if you do that, then it does affect the cylindrical geometry and causes extra loss. The way to solve that problem is with what's called loose tube buffer. And you can read about that in the text. There's a paragraph or two about that effect. So those are the main effects. And really the place to go to really get the nice summary of this is figure 5.9 in the text, which shows, hopefully that's not too bright, maybe that's better, which shows that as a function of wavelength, attenuation as a function of wavelength, both of them on logarithmic scales, showing that at short wavelengths, glass absorption in the ultraviolet is here. At long wavelengths, we have glass absorption in the infrared. That was the first effect I talked about, absorption, which occurs at both longer and shorter wavelengths, leaving us that window in the 1.6 micron range. And then scattering losses, which are also increasing for shorter wavelengths due to the lambda to the -4 functional characteristic of Rayleigh scattering. And in between there is this little window in this range of 1.5 to 1.6, 1.3 to 1.6 microns, where the loss is actually quite low, and in fact going below 1 dB per kilometer, approaching 0.1 dB per kilometer, but more or less not getting much below about 0.25 dB per kilometer. The other effect that you have to be aware of in optical fiber loss is the OH absorption peak. This is separate from the three, well, it's part of the absorption, okay? So I should say as part of the absorption we have OH absorption. At 1.4 microns wavelength. And that's simply a resonance of the OH bond to that wavelength of light. That wavelength of light has a photon that has the energy just right to excite that bond. Think of two masses on the end of a spring. And so we have this very low loss area, but right in the middle of that we have the OH absorption peak with a high loss peak. And it's due to water impurities in the fiber. And modern fiber, sometimes called full spectrum fiber, available from Corning, has essentially eliminated the water peak. They've got such careful control over their manufacturing process that the water peak has been eliminated. Okay, so that's the overview of loss types. This graph sort of this plot sort of shows it all. And thank you.